Hello everyone, today we're going to go over the concept of a pseudometric space in analysis. Now this is a pretty non-intuitive concept, and it's a pretty weird one in my opinion. So I'm really excited today to show you guys the cool properties of this irregular space. So without any more further ado, let's begin. So before we get into what a pseudometric space is, I wanted to talk about what a normal metric space is. So what is a metric space? Now, I already made a video about what metric spaces are. You can find that in my topology playlist. So this is just a brief rundown of what a metric space means. So a metric space is just a set X equipped with some distance function that we call the metric, where the metric satisfies the properties where it's symmetrical, distance between x and some y, where I should note that x and y are in some larger set big X. So the distance between x and y, that is the distance between y and x. The distance between x and y, it's non-negative, meaning that it's between 0 and infinity. Also, if the distance between x and y is 0, that implies that x equals y. And then we have the a bit more non-intuitive triangle inequality. The distance between x and y is less than or equal to the distance between x and some other point z, plus the distance between z and some other point y, and talk about the motivation of this concept in my metric space video. So these are our 4 axioms of a metric. If our function satisfies these properties, doesn't matter what function it is, as long as it satisfies these 4 axioms, bingo, we have a beautiful metric space. Now, the pseudometric space is really similar to this concept, a pseudometric space. So just like the metric space, it's just symmetric. It's more of a, should I say, a generalization of the metric space. So I have some set x equipped with some distance function d, like before. It's symmetrical along the inputs, like before. Also, this is obeyed. This is the distance between x and y. It has to be non-negative. But this is where it gets a bit strange. I'm sure this is going to throw you guys off a bit. But the distance between x and itself is 0. Okay. And then we have the triangle, the normal, regular triangle inequality. So xz plus distance between c and y. Sorry for all the shaking. So yeah, now this is a bit strange, right? Because we no longer have the distance between x and y is 0, and that implies that x equals y. We just have the distance between x and x is 0. This means that it is possible that we can have 2 points that aren't the same that have distance 0. So in other words, this does not imply, it doesn't imply, out of all our rules of the metric, this doesn't imply that the distance between x and y being 0 implies that x equals y. That's no longer the case. Now, it is possible that that can be the case, but it isn't an implication from this rule. So it is possible to construct a metric space where you have 2 distinct points that have 0 distance. That's so odd, because let's draw some general set x. I give 2 distinct points, a and b, in this set, and we think that it should have some distance, but for some metric, it's possible to have these 2 points have 0 distance from each other whilst not being the same point. So you guys may be wondering, well, for what possible metric can I construct? What possible formula can I make where the distance between these 2 points is 0? And let's do that. But before we do that, I want to emphasize this. The pseudometric space is a generalization of the metric space. In other words, all metric spaces are pseudometric spaces, but not all pseudometric spaces are metric spaces. Now, this is a bit non-intuitive from the definition, because pseudo means false or fake, so they should have changed the word for it, but that's how it works. So you can have a pseudometric space where the third axiom does hold, but the other way around doesn't have to be true. You can make a pseudometric space that doesn't have the third axiom of a normal metric space. So let's give an example of a proper pseudometric space that has 2 points that are the same, that have 0 distance from each other. Okay. So here is a nice example. So let's just find a set X. Set X is the set of functions. The set of functions, should probably put that dot bit further up. So a set of all functions that take in some value between the interval 0 and 1 and map those on to the real numbers. So it just takes some input between 0 and 1, the closed interval, and just assigns it some real number. Okay? Such that the function is, I believe it's called Lebesgue integrable. That's the definition for our function. Now, this is a pretty weird set because we don't have the normal Riemann integral. Instead, we have the Lebesgue integral. I believe that's how you pronounce it. The Lebesgue integral. We have the Lebesgue integral. Now, this integral isn't the exact same as the Riemann integral, but for most cases, it is the same. So if our function is continuous, the Riemann integral and the Lebesgue integral evaluate to the same thing. So then why do we use this Lebesgue integral in the first place? Well, because it turns out that the Riemann integral, let's actually write this out. So just have the Cartesian plane. Now the Riemann integral doesn't actually work. It isn't well defined for sets that are uncountably infinite and are not continuous. The Riemann integral isn't well defined for that. So say I have the set of, well, I don't know. So you have the set of rationals, okay? Or wait, better, a set of rationals, okay? And I have a function that assigns each member of that set some value, okay? And it might look something like this. This function, it wouldn't be Riemann integrable, since this function, the domain of this function, includes an infinite set. So the Riemann, specifically, it's the irrationals that are incountably infinite. But since this function is selecting out of those, how do I say this? This function is picking out the rationals from the entire real number line. The Riemann integral no longer is well defined for that concept. So that's why we introduce a new integral called the Lebesgue integral that can treat this situation very well. So you have the x has to be it's a function that just takes the interval 0 and 1, takes a point in that interval and maps it onto the real numbers, and it has to be Lebesgue integrable. Now there's more nuances in what it means to be Lebesgue integrable, and that gets into the depths of measure theory, which we aren't going to go. We're not going to dive into that subject much today, but that's the more nuances of it. So yeah, let's start. Let's define a function on the set. Distance between f and g. Let's define the distance between the two elements of the set x. because we have a set of all these functions. So I guess I should draw this out. Here's 0, here's 1. Just have this set of all the functions. So here can be f, here might be h, here can be m, here can be L or something. You have a set of all the functions. You can even have non-continuous functions. Like you can have piecewise function. You have any kind of function you want. And the distance between two elements is going to be the integral from 0 to 1, of course, of the modulus, the absolute value, of f minus g dx. So remember that this integral is the Lebesgue integral. So let's check if this satisfies the properties of our pseudometric space. So first of all, does the distance between f and g equal that of g and f? Well, the integral from 0 and 1 of modulus of f minus g dx, that just equals the same thing, but g minus f dx, because we have a modulus sign here. Like if I have the modulus of minus 3, that's just equal to 3. Okay, the modulus kind of reverses the flip in a way. So these are indeed the same. 2. Is it non-negative? Is it non-negative? So is this between definite 0 and bounded infinity? Well, the answer is, of course, yes. Like, even if you have a function, here, let's just begin a graph. I have 0 here. I have 1. Even if I have a function that like goes down here, of course the area is negative, but I have the distance between two of these functions. Now, the distance between two of these functions, it's going to be this one minus this function that's negative. But I take the absolute value of that, and I'm going to get a positive number. So, of course, I'm always going to get a positive number, since the integral of a positive function that's bounded will always converge to a positive number. 3. Okay, so there's also the triangle inequality that we can prove. Now, I won't actually be proving this inequality. I'm going to leave it as an exercise for the viewer, simply because I don't want this video to be too long. What you do is you just write them out as integrals. You just use properties of like moduluses and inequalities, and you can prove this statement. Sometimes though, the triangle inequality can be a bit difficult to prove. You have to make use of other theorems like the Minkowski inequality and stuff to prove it. This is not one of the cases though. Just a side note of that. And then the cream of the crop, the thing that we want to study today, is that the distance between f and f equals 0. Again, this does not say that the distance between f and g is equal to, or implies f equals g. It just says that the distance between f and f is 0. And of course, this is trivial to show. Let me just move the paper up a tad bit. I have 0 to 1, the integral modulus f minus f dx, and that's 0, right? The integral of 0, the area under 0 is going to be 0. Now you're probably wondering, well, okay, well, for what functions does f minus g equals 0, but f does not equal to g? I could try many functions, but like if I try, say, f of x equals x squared, defined on this interval, and I have f of x equals 2x defined on this interval, like the distance between these two distinct functions it isn't 0. They have positive distance from each other. So like what function? Like it looks like for the majority of the cases, this metric space, this pseudometric space, is just a regular old normal metric space. Now there is a function though. There are a set of functions that we can use show that this space isn't exactly, well, we've already shown it by the metric, but there are functions that we can pick out where the distance between them is 0, but they're not the same thing. So for simplicity, let's use the function, let's just draw another graph. Let's use the function g of x equals 0, defined on 0 and 1. So here's 0, here's 1, it's defined on 0 and 1. Note that it isn't 0 past this, beyond this, okay? It's bounded. It's undefined for points outside of this. Like, I want to make that very clear. We're only talking about, this should be a sharp bracket of it. We're only talking about the set of functions on this bounded interval. So here's g of x, and let's draw, well, first of all, we have to define what f of x is. So let's define f of x as, what's it called again? It's the indicator of the rational numbers. Now you guys may be going, ooh, what does that mean? The indicator of the rationals. Well, the indicator of the rationals is just defined as 1 if x is a member of the rational number, so if x is rational, and 0 if x is irrational or just not rational. And of course, this is also defined on the interval 0 and 1. Keep trying the end bracket a bit weird. But yeah, so you probably see why this is called the indicator, because it picks out, kind of selects out what, I keep saying, it selects out the rational x values, said it again, wow, it selects out the rational numbers and it maps it to 1, and this is why it's an indicator. If it's 1, it indicates that, oh, x is rational. If it's 0, it indicates that x is not rational. You can think of it like a binary code. Like if it's 1, like you have some machine, you put the x in the machine. If the machine turns on, that's represented by a 1 in code. 1 is on, 0 is off. So if it shines, if it blinks, it indicates that x was a rational. If it doesn't do anything, that's like a 0, it's off. It means that x is irrational. That's what's called the indicator. It selects it out. It's map it to 1. I spent too much time talking about this. But so the most important property of this thing is that it's not continuous. So let's just draw it out. So f1, it's not continuous, right? Because like not all numbers between 0 and 1 is irrational, nor irrational. So it's gonna look something like this function will look something like this, and you just have some points at the x-intercept too. So I hope you get why that is, because like think of like the rational numbers. Okay, here's like you have 1/2, you have 1, you have 3/4, you have 0.372891, and then irrational numbers like 0. Or like the square root of like 1/2. I'm sure that's irrational. So you have these irrational numbers as well between 0 and 1. Now for the rational numbers, it's gonna project it to 1. All of this should actually be over here. I drew it wrong. I didn't draw it wrong. It doesn't pay that much attention. So here's 1. Here's g of x. Okay, here's g of x. And here's like 1 here. Now, so f of x is gonna look like a bit choppy. So it's not continuous, right? Because it's not like all the points between 0 and 1 maps to a rational. It's not gonna all. I did it again. Gosh. Here, let's just. Okay, this is 1. Here's 1. Okay, I'm drawing the dotted lines like below 1. So let's just rename this one to be 1. Should have done it with this one. So it's not going to be a straight like golden line. I'm going to have some points at the 0. Those points being the irrational numbers. But when x is rational, you're gonna get mapped to 1. So it's gonna be choppy like that. Okay? And it's gonna be, this is a bit, I know I'm being a bit vague here. It's really hard to actually draw what this function is. And that's because the rational numbers are a dense subset of the real numbers, which means that I can, like, any point on the real number line, any rational there, I can show you, like, I can take any open interval, like it's have like some, this is like 1/2, right? Like any rational, I can take any open interval around it, and I can show you an irrational that's in that interval. I can show you that because it's a dense subset of real numbers. You can prove that rigorously, but it basically says that the irrationals are always infinitesimally close to rational numbers in that kind of vague sense, but it's more rigorous than when we use open balls and stuff. Basically, the irrationals are limit points of the rational numbers. So that's why it's a bit hard to draw, because I can take any point here. I can find like an infinitesimal point that maps to 0. Okay, so let's find the distance between these two functions. So here's f of x, here's g of x over here. F of x, some points are above here, some points are down below. The distance between them, let me just, the distance between these two guys, first there's going to be the integral of, the big integral, 0 to 1, f minus g dx, okay? Now, g is, of course, 0, so this is just the integral. I'm going to write it down here. Just the integral of the modulus of f of x, from 0 to 1. The Lebesgue one, by the way. I'm stressing that a lot because it's not defined for the Riemann integral. You have to evaluate what this is. Okay, so how do we go about doing that? How do you evaluate the Lebesgue integral? Now, this isn't going to be the best explanation, because we're not going to go deep into measure theory in this video. I don't want to go deep there because, I don't know, like, I want to stick to the normal functional analysis that we're doing here. I don't want to go deep into measure theory. It's a bit more abstract, so I don't want to overcomplicate things. I'm rambling now, but to evaluate the Lebesgue integral, what we do is we use something called a measure of, like, an interval. So this is like a really simplified, like, notion of it, but basically the measure, I can have some open interval, like 1, 0, for example, a set of points between 1 and 0, and the measure of 1 and 0 gives me the size. It gives me the size of this open interval, and that size is 1. It just picks out an interval and just gives it a size. It's 1 because we have 1 minus 0. Okay? Or wait, really, this should be 0, 1. It goes left to right. Okay? And, like, you can kind of prove theorems about the measure function yourself. It's really intuitive for, like, the basic things, like the measure of, say, the point 1, 3 and the point, wait, what's this sign again? Yeah, you take the unions of, these aren't points, sorry, these are intervals. You take the union of, like, intervals, here's maybe 4, 5, that corresponds to doing 3 minus 1, and then plus 5 minus 4, put brackets around these guys, 3 minus 1 is 2, 1, you get 3, that 3 is the measure of the union of these intervals, okay? And then you can generalize this to, like, infinite number of unions and stuff. So that's what the measure function does. It picks out some interval, gives you a size of the interval. Now, intuitively, the measure, this is specifically called the Lebesgue measure, by the way. The measure of a single point, though, not of a single point. Well, yeah, it's a single point. But what's the measure of a single point? So, like, if I have, so here's an example. Here I have, like, say 2 and 3. I can have the interval between 2 and 3. That's like this. And now, what about the interval between 2 and 2 and 1/2? That's this. Okay, it gets smaller. What about the interval between 2 and, say, 2 and 2.0005? Well, that gets even smaller. It gets smaller and smaller. The intuitive concept, you can prove this rigorously. I'm just going to give you the intuitive notion of it. You can have the open interval between 2 and 2.0000, like a billion zeros in one. That's really, really close to 2. And then you just have 2 itself. You just have like the point 2. And this is all for the real line, by the way. It generalizes just the other, like, complex numbers, but this is just for the real line. So you have 2, and 2, the measure of 2. You don't have any interval now. Well, really, your interval, you do have an interval. Your interval is, your interval is 2 and itself. Okay, it's 2 and itself. And the measure of that interval is going to be 0. Okay. So if I have a single point, the measure of that point, the Lebesgue measure, is 0. And like this is like for any point. And of course the union between these, like the union between these intervals, we just like take like this minus this plus this minus this and stuff. So similarly, the union of points, the measure of that is also going to be 0, right? Because if one point is measured 0, the other point is measured 0, what's the union of these 2 points? So that's also measured 0. Since I might have 2 and 2, I might have a measure of 2, 2, and like 4, 4. Well, that's just going to be 2 minus 2 plus 4 minus 4. But the measure really is the measure of 2, 2 plus the measure of 4, 4. Both are 0. We get 0, right? So if it multiple points, the measure of each point is 0. So maybe you might be wondering why we care about measure. Why are we saying this? This is so off topic, but it's actually not. Because the Lebesgue integral, to evaluate that, we have to take the measure of the function. So for this function, we have the function here, right? The Lebesgue integral of this function it's going to be the union of. It's really just going to be the measure of the function, kind of. It's the union of the measure of each element of that function. But each element of the function are points. So they're not smooth. They're not smooth like functions. So the measure of each individual point just union all together to have like an incalculably infinite number of these disjoint points. It's gonna be 0. So the measure. So this is really just the measure of this function, and that's going to be 0. I hope that made sense. So to evaluate the Lebesgue integral, we just take the measure of each point. And you guys might say, okay, well, then why isn't g of x 0 when you evaluate the Lebesgue integral? It's made of points, but these points are connected. They're all in one piece. With these points, you have an incalculably infinite number of them, like all lined up together. But for this function, remember that the rationals are countably infinite. So when the measure function acts on each point and unions them together, you're gonna get 0. So the distance between f of x and g of x is 0. Now note that f of x and g of x, they're not the same function. They're almost the same function. In math we said see that they are almost the same, approximately the same, because there are way more irrationals than rationals. We're getting into number theory now, but there are way more. There are an uncountably infinite number of irrationals, but a countably infinite number of rationals. So these functions, like for f of x, most of the points, like most of this number of points, kind of becomes a bit wishy-washy, vague. But most of the points are along this x-axis. They're along y equals 0 from 0 to 1. But some of the points, compared to almost all of them down here, are up here. So it's almost the same, but it's not exactly the same. Therefore, we have two distinct functions where the distance between them is 0. Hence, the pseudometric space. This would be way better if I found it, hence the pseudometric space. So yeah, that's what the pseudometric space is. I hope this video made sense to you guys. The pseudometric space it's a really cool space. It ties into measure theory a lot, which I'm sad that we couldn't get much into today's video. Like, the reason why I didn't want to get into measure theory that much is that it's a pretty abstract topic. I don't want to make my videos too complicated. Maybe I will. Like, I will do that, but I might make a playlist in the future about measure theory. But yeah, those are pseudometric spaces. I hope you guys had a great day. Yeah, that's pretty much it. Bye.